welcome to our February meeting and our February lecture. I'm Mary Jo Fresh. I'm chair of the steering committee this year. My honor to introduce Terry. Terry Miller earned his undergraduate degree in chemistry from the University of Kansas. After receiving his PhD from Cambridge University as a Marshall Scholar, Terry went to Bell Laboratories, where he became a distinguished member of technical staff. Thereafter, he moved to The Ohio State University as the first Ohio Eminent Scholar Professor. He has held visiting faculty appointments at Princeton University, Stanford University, and the Institute for Molecular Science in Japan. Terry's research centers on the spectroscopic identification, characterization, and monitoring of reactive and or trace chemical species. He has developed numerous highly sensitive spectroscopic techniques spanning frequencies from the microwave to the ultraviolet. Presently, his work focuses upon laser-induced fluorescence and cavity ring-down spectroscopy of reactive intermediates. Particular targets include intermediates that play critical roles in a variety of processes of interest to our society and economy, examples of which include combustion, atmospheric chemistry, and plasma processing of electronic devices. Terry is author of more than 350 scientific publications. His research has been recognized with the Megers Award of the Optical Society of America, the Bowman-Michelson Award of the Koblenz Society, the Burke Medal from the Royal Society of Chemistry, the Breda Prize and Plyler Prize of the American Physical Society, and the Johannes Marcus Marcy Medal of the Czechoslovak Spectroscopic Society. He has been granted the recognition of Fellow by the American Chemical Society, American Physical Society, Optical Society of America, American Association for the Advancement of Science, and the Society for Applied Spectroscopy, which also has granted him its highest award, honorary membership. He currently serves as editor-in-chief of the Journal of Molecular Spectroscopy, and for 22 years was the chair of the International Symposium on Molecular Spectroscopy. He sits on several other journal editorial boards and conference program committees and chairs the advisory committee for the International Free Radicals Symposium. At The Ohio State University, he serves as convener of the President's and Provost's Advisory Committee. I want to add that Terry was a founding member of the Emeritus Academy and our first chair of the steering committee. Please join me in welcoming Dr. Terry Miller as he presents the spectroscopy of molecules that affect the quality of your life.
Thank you, Mary Jo, for that very kind introduction. Can you hear me in the back? Okay, so I'm going to leave the second of my microphones off. If you have trouble hearing me, let me know, okay? I have so many wires on me right now that I sort of feel like I should be in a Tom Cruise movie. But I'll try to proceed. I want to thank all of you for coming out this afternoon for this talk. The title is The Spectroscopy of Molecules, whose chemistry can affect the quality of your life. And this title also serves as a mini outline or overview of my talk. I'm going to begin by telling you a little bit about the fundamentals of spectroscopy and a little bit about the historical development of the science. Then I'm going to move over and talk to you about some of the molecules that we have studied in my laboratory, which we in fact have chosen in part because their chemistry can affect the quality of your life. And to wrap things up, I'm going to show you some actual spectra from our laboratory and try to give you a feeling for the excitement that I, as a spectroscopist, feel when we analyze some of these spectra. And so the first slide here, in fact, lays the basis of spectroscopy. Spectroscopy is the interaction of electromagnetic radiation. The visible part of that is the light, which is visible, which you can see, with matter. And we're going to restrict the matter today to molecules or atoms. And we're not going to distinguish a lot between atoms and molecules. We'll simply treat atoms as monoatomic molecules. Spectroscopic experiment basically consists of three aspects. We have to have a light source, electromagnetic radiation source. We have to have a sample, for today's purposes, of molecules. And we have to have an analyzer of the light. We'll talk a little bit more about that later. And a detector of the strength of the light that comes through. In this particular diagram, the analyzer and detector are one piece. They can be separated. The analyzer can be put between the source and the molecules. There are various configurations, but these are the three main components. From a historical point of view, most folks start from about 350 years ago, experiments by Isaac Newton. At that time, light sources were limited basically to the sun. And so what he did was he had a window in his room. He had curtains across that window, and he made a little hole in the curtain and let a light beam or a sunbeam through. He then passed that sunbeam through a glass prism, which served as his light analyzer, and projected the image after the light passed through the prism onto the wall of the room. And so the next slide shows what happens when light passes through a prism. You can see we start out with white light here, and then it enters the prism, and the colors separate. This is the same sort of effect that we see after a thunderstorm. When we look at a rainbow, we see the colors of the spectrum, and in that case, the prism are the small little droplets of water in the sky. So if you project this on the wall, now you'll see something that looks like that, and so I've labeled this what Newton saw. But this is 150 years later. This is Fraunhofer's experiment. And to me, this is really the first spectroscopic experiment. And the reason why I call it the first spectroscopic experiment, even though the apparatus looks almost the same, Fraunhofer noticed something which Newton did not. He noticed these dark images on the spectrum. You can see them here against the colors, and they're outlined here more clearly. Those dark images surprised him, and frankly, he didn't know where they came from. We now know that they were the missing ingredient in Newton's experiment to make it a true spectroscopic experiment. He had to have a sample. Well, the sample, in this case of atoms, was there for Newton too. It was in the upper atmosphere of the sun, atoms and ions, which could absorb radiation. But even though this will be remembered primarily as the first spectroscopic experiment, it should also be remembered as the first practical application of spectroscopy. And the reason why Fraunhofer repeated Newton's experiment was because he was a glass maker. And obviously, the quality of glass making had improved in 150 years. And he was interested in trying to actually do quality control in his little glass-making factory. And the best way he could measure the quality was to disperse the spectrum and look and see how clearly he could see the color changes in the spectrum. Right? What he realized after he saw the dark lines, that they were very sharp, and that by looking to see exactly how sharp those lines were, he could measure the quality of glass very much more accurately than he could ever measure it from looking at these diffuse colors blend into one another. So now that we have the basic spectroscopic experiment in front of us, let's look for just a little bit at some of the component pieces of it. The electromagnetic spectrum. Here's a diagram which shows the electromagnetic spectrum. It extends all the way from X-rays, gamma rays, from radioactive sources, all the way to the radiation that comes out of electrical power lines. In between, you find radio frequency, where your radios and TVs work, microwaves, cell phones, the sun, so on and so forth. The most important thing here is that you will see that the light or the electromagnetic spectrum is represented by this wave pattern. Okay? If you remember when the white light passed into the prism, we saw those waves propagating through the prism and then eventually onto the wall. And let me tell you a little bit about the characteristics of this wave. Like any wave, like the waves, if you throw a rock into a pond or you're on the beach and the waves coming in, you will see them moving. The big difference between electromagnetic radiation and the waves in the pond is the waves in the pond needs a medium to propagate, in that case water. Electromagnetic radiation can propagate through a vacuum, so it can come from the sun to the earth. All right? But in terms of a wave, same characteristic. The separation between these maxima is called the wavelength. It can be measured in feet, inches, microns, nanometers, whatever you want. So that's given the symbol lambda. It has a frequency, which we call nu, and the frequency is determined by, if you're an observer here, and count the number of these maxima that pass by you in a given length of time, say a second. All right? And this relationship is very important. The frequency is equal to the speed of light divided by the wavelength. Okay? So now we're going to be looking at using this part of the electromagnetic spectrum to do molecular spectroscopy. We're not going to do molecular spectroscopy down here. We're not going to do molecular spectroscopy up at this end. One thing that I should bring up now is that you might say, well, you're talking about electromagnetic radiation as a wave, but didn't Einstein demonstrate in the early 20th century and receive the Nobel Prize for showing and explaining the photoelectron effect in terms of light as a particle or a photon? Right? So there is this sort of wave-particle duality. There's been a lot written in the hard science world and the not-so-hard science world about this quantum physics mystery or duality. Basically, the point is that if you have small particles very close together, they don't obey classical Newtonian mechanics, all right? They obey quantum mechanics. And in quantum mechanics, you will have this wave-particle duality. A thing we can do in terms, a useful thing we can do in terms of thinking about light as a photon is to recognize that the energy the photon carries is equal to a constant, Planck's constant, times the frequency, or using that equation relating wavelength and frequency, h times c over lambda. So now what I'd like to do is talk about our sample. And we're going to talk about our sample in terms of the simplest monoatomic molecule, the hydrogen atom. And this is a picture of the Bohr model of the hydrogen atom. And there is a proton in the middle, and there's a single electron circulating around it. If Newtonian mechanics held, that electron could circulate around in any orbital it chose, and if it got more and more energy, the orbital would simply get bigger and bigger. All right? But quantum mechanics says that that cannot happen, that there are certain quantized energy levels, discrete, well-defined energy levels in which the electron can circulate around the nucleus. Once again, ultimately that goes back to the fact that you can think of the electron particle also as a wave. And so the Bohr model, which is a highly accurate model for the hydrogen atom, does in fact lay out what those energy levels are. And these are spectroscopic transitions between those energy levels in the ultraviolet, visible, and infrared. And one can absorb a photon and push the electron up, or an electron in an upper orbital can emit a photon and drop back down. The key thing that makes spectroscopy work is that energy is conserved in this process, that the energy between these levels has to be equal to h times nu. And because these are discrete levels and non-continuous levels, it means that there will be only certain frequencies that the atom or molecule will absorb. It can't absorb the continuous spectrum. Certainly the hydrogen atom cannot. All right, so this is referred to as an electronic spectrum because the energy is being exchanged between the photon and the electronic degrees of freedom, with the separation between these levels determining what frequencies are absorbed. If we go to a molecule, things can get a little bit more complicated because molecules have more degrees of freedom. They have electronic motion like atoms, but they also have more than one nuclei. So you can have vibrational motion of the nuclei and rotational motion of the nuclei. And these also result in quantized energy levels. So let's see how that works. Here are schematic diagrams of the three vibrational modes of water. This is the oxygen atom, and these are the hydrogens, stretching symmetrically and asymmetrically, and scissors motion. And now the resulting energy level diagram will consist of electronic states, ground, first excited, second excited. But upon each one of these electronic states, we will have a vibrational manifold because the molecule can absorb both electronic energy and vibrational energy at the same time. This means where in the atomic spectrum we had a single line, here we might have half a dozen lines. Right? Now, the molecule can also rotate in space, and here is example of that, rotating about two orthogonal axes, and that motion is also quantized. And so that gives us, if we look at an individual vibrational level, a set of rotational levels which are superimposed upon it. And here we might have 10 or 20 rotational transitions for each vibrational line. So we've now multiplied up the complexity of the electronic spectrum of the atom by a factor of at least 100 and maybe 1,000, or if it's a big molecule, maybe 1,000,000, but we're not going to go there today. So hopefully at this stage I've given you a little bit of an idea of the fundamental principles underlying spectroscopy, and hopefully I haven't given you more than you ever wanted to hear about those fundamental principles. But I would like to point out, and I'm sorry, the transitions within this level occur, within the rotational levels, occur in the microwave region. Going back to this business about, I've given you perhaps more than you want to hear, I'd like to point out that these quantum phenomena are becoming more and more important these days. This is a picture that was released by the White House just before Christmas when Donald Trump signed the National Quantum Initiative Act. And in fact, I personally think that's a very important piece of legislation it was motivated by the technological potential of quantum computers, all right, which could be orders of magnitude faster and more efficient than the computers which we have now. But it also recognizes the importance of quantum phenomena in a wide variety of scientific experiments and results. I must say, after looking at this picture for a few minutes, I was reminded of the tagline from some of the old Geico commercials, and something like this. All right, so now both President Trump and the entire audience knows enough about spectroscopy and quantum physics that we can proceed. And so let's proceed with a diagram which I created a few years ago that sort of summarized the research that was going on in my laboratory. First of all, this is the Fraunhofer experiment, which is symbolic of simply a spectrometer or spectroscopy in general. And from that spectrometer flows spectra. And here are some spectra which we took in the laboratory, small organic chemical intermediates. You notice that they have the same empirical formula, but the spectra look quite differently. One is labeled T and one is labeled G, meaning that their structural formula is different. Now, in a very real way, there is an analogy between these spectral lines for molecules and DNA for humans. That if in fact one has your complete DNA sequence and you understand entirely how the genetic code works, you have a very good opportunity to predict how your body is going to behave and the characteristics of it and the possibilities for disease, etc. Well, if you have an understanding of these individual spectral lines, then you have the opportunity to combine that with large electronic structure calculations that Russ Pister has pioneered here at Ohio State and been pioneered around the world, to calculate things called potential energy surfaces, which in the limit will allow us to predict how individual molecules react with one another, their rates and their products, etc. We're not there yet, all right? But we have made strides in that direction. The other analogy is with DNA, is that of course it's a great tool for identifying people. Well, these spectra are a great tool for identifying molecules. And there are places where you really, really want to identify molecules in low concentrations, in situations where there are many similar molecules around, and you want to know exactly which one it is, even what its structural formula is. And I've got down here 3 examples of that. One of them is in the lower right-hand corner. There are now numerous radio observatories that are recording lines from molecules in interstellar space. One of the great questions of the 21st century is whether these molecules are relevant to the formation of life on Earth or elsewhere in the universe. That's probably not going to be a question that will affect the quality of your life today or tomorrow, but it is a question for the 21st century. What probably could affect your life today or tomorrow are these 2 examples that involve the oxidation of hydrocarbon molecules. Hydrocarbon molecules are the things that come out of oil wells, that are in your gasoline, fossil fuels, etc. And here the candle symbolizes combustion reactions, where one generates power in electrical utilities or in your automobile engine, etc. And down here, which is a picture of a smoggy afternoon in a Chinese city that I will remain unnamed. So let's look at the processes that occur with these two oxidation processes of hydrocarbon species. And the little boxes here correspond to particular molecules that we have observed the spectra of that are involved in these particular examples. And up here, these are the ones that are particularly relevant to the theoretical interpretations. So here is a mechanism, a proposed mechanism, the tropospheric oxidation of saturated hydrocarbons. Now you might say, why do we have to worry about hydrocarbons in the atmosphere? Well, RH is shorthand for a hydrocarbon, and the hydrocarbons get there from what are called volatile organic compounds. Each year, there is a tremendous amount of volatile organic compound ejected into our lower atmosphere. Approximately 1 billion metric tons of organic compounds are ejected from biological sources. Another 150 million from anthropogenic sources, from gasoline, petroleum refineries, and things like paints, coatings, etc. So there's a lot of this up there. And now what's the chemistry? Well, sunlight can generate hydroxyl radicals, OH radicals, which pull a hydrogen off of an alkane. The alkyl radical is very reactive. It combines with oxygen and produces a peroxy radical, which then can convert to an alkoxy radical. And many of the species I showed you on my previous slide that we have studied belong to these two families of radicals. And so now I can blow this up, add a little color to the diagram, and if we start out here at this key intermediate, the peroxy radical, we will see that it reacts with NO, which can be generated in automobile engines in large amounts, and pull off an oxygen to produce RO and NO2. NO2 can be photolyzed by visible light from the sun. And when it's photolyzed by that visible light, it produces an oxygen atom. The oxygen atom combines with O2 to make ozone, which is one of the, probably is the most toxic ingredient in photochemical smog. And this process is responsible for about 85% of the smog, whether it's in China, the LA basin, what have you. All right? So, yes, we might be interested in trying to observe RO2 and RO radicals under those conditions and benchmark the chemistry that takes place so that we can have reasonable regulations that minimize that kind of chemistry while at the same time don't simply shut down all our factories. This is a nighttime view. We're not going to go into that. Let's go into the burning candle or the automobile engine. There we have fuel coming in. OH radicals again produce the alkyl radical, combines with O2 to make RO2. But now you notice that this chain reaction has termination steps up here and propagation steps down there. Generally, if we've got fuel in our car, we like the combustion reaction to propagate, so we'd like for things to go down there. But we can only get them to go down here if we have the RO2 turn into the QOOH. And this shows you what's actually happening. RO2 has a structural formula like that. QOOH transfers a hydrogen and has a structural formula like this. We're going to come back to this point a little bit later, so you'll have a test on it. So now let's go back to this diagram, and I'm going to be very brief here. I'm simply going to tell you that while I would really like to talk about all the molecules here, I'm going to restrict myself to talking about one of the molecules here, methyl peroxy, and some of the larger. That's the simplest one, methyl peroxy, and then some of the larger organic peroxy radicals. All right, so how do we take a spectra in this day and age of this sort of species? Well, here's the experimental apparatus for looking at molecular absorption spectroscopy of species like this. Today, we don't use the sun for a light source. What we do is we use lasers for a light source. And these are one laser pumping another laser, which can give out various colors of light. We can use nonlinear processes to shift that light from the visible region into the infrared region where this particular molecule absorbs. And we'll put, we end up with a couple of millijoules of energy in a pulse of photons and a line width of about 5 gigahertz. 5 gigahertz, by the way, is the sort of frequency that the wireless phones in your house work on. We're not talking about this light being of a frequency of 5 gigahertz. It's in the infrared. But the bandpass of this light is 5 gigahertz. We then send this into an optical cavity formed by 2 highly reflective mirrors. Why do we do that? Well, we've got a limited number of molecules in here, and we're going to pass photons through. Well, I've already argued that molecules are really small. Photons are even smaller. And so there's a pretty low probability that a photon and a molecule are going to collide in a single pass. All right? Most of the photons will go right through if you didn't have another mirror here. But we don't want to waste those photons. We spend a lot of money to generate them. And so what we're going to do is we're going to turn them around, give them another chance, bang them into another mirror, boom, 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 boom. All right? The mirrors that you have at home in your bathroom have about 95% reflectivity. The mirrors that we're using in this experiment have up to 99.999% reflectivity, 5 nines, okay? If we had to have the total path length that we get from bouncing them back and forth in a single tube, all right, that tube would reach from here to Cleveland, a 50-centimeter tube in the laboratory. So this gives us a tremendous increase in sensitivity. So this is our spectrometer, but we've got to do some chemistry. We've got to produce those methyl peroxy radicals, and we're going to start that process off with photons from an argon fluoride excimer laser, rather than the sun in this case. And this is the detailed chemistry that goes on. I'm not going to go through that. Simply, this is the alkyl radical that is produced in our atmosphere from sunlight. This is the oxygen. This is the combination to make the peroxy radical. All right? So now we're going to take a spectrum. And here, in fact, is the spectrum of the peroxy radical in the near infrared. This is the origin of an electronic transition. This is vibrational structure on that electronic transition. This little line down here corresponds to a bending of the carbon-oxygen angle. And over here, this corresponds to a stretching of the 2 oxygens with respect to one another. There are a couple of other things that I want to just point out in this spectrum, and then we'll come back to. The first one is that these are not single lines like Fraunhofer saw in his spectrum. There's structure to those lines. We already resolved the electronic structure, resolved the vibrational structure, but we have not yet resolved the rotational structure. Okay? The other thing is there's other lines here which I haven't marked until now. These all have zeros on the bottom, and that means they start out in the very lowest energy that the methyl peroxy radical can have. These spectra, however, are taken at room temperature, that's the RT, and there are levels other than the lowest one populated. There are vibrational modes with one quanta of nu 8, one quanta of nu 12, this is nu 8, etc. Okay? We're going to come back to that point later on. So now we've got our spectrum. Here's what happens when we move on up to an ethyl peroxy radical. Once again, we have the same general features: an origin, a COO band, vibration, and OO stretch vibration. However, in this case, rather than having one line, we have two lines, but I've just got one molecule. Well, what's happening again is I've got some different structural conformers of that molecule, and we can tell the difference spectroscopically between these two geometric entities of the ethyl peroxy radical. Now, what can we do with spectra like this? Well, one of the things that we can do is we can use them as benchmarks for the sort of calculations, electronic structure calculations, that may one day allow us to predict a lot of chemistry without doing experiments. And here is a series of those species, about a dozen peroxy radicals, and here are the frequencies of the electronic origin bands. And we can try to match that against calculated frequencies. And I'm not going to go through this in great detail, but there's about 8 calculations, a big difference, almost factors of 2, depending on which one you look at. Turns out that if you compare the G2, boy, you really do pretty well. This is the difference, better than 1%. And so this one clearly gets the silver medal. And over here, but it's a relatively expensive calculation, so if you want the value choice, you go with the, you go with the density functional calculation. However, the calculations at this stage are not yet good enough to answer some of the questions that we think our spectra can answer. So let me show you how we can do some empirical things not involving calculations. First of all, we can make what we call a spectral structural diagram, in which we label this axis with the number of carbon atoms in the peroxy radical, and this axis is the frequency of the transition. And now we can draw some inferences from that. If we take and fix the number of carbon atoms at 4 down here, then we see that we can have an isomer, what we would call a straight chain isomer with the O2 moiety on the end, which has an origin frequency just below 7,400 wave numbers. If we put the O2 moiety along the chain, it goes from a primary to a secondary isomer, and the frequency jumps up by a couple hundred wave numbers. If we branch it out even more, a tertiary substitution for the oxygen moiety, it goes all the way up to here. Whereas if we branch at the beta carbon, the frequency goes down. We take this straight chain peroxy and put a branching here, then the frequency drops by about 100 wave numbers. So these structural relationships allow us to assign spectra that we couldn't do on a fundamental theoretical basis. And so with that diagram, we can attack a practical question. and that concerns gasoline. And here is a plot of the percentage of hydrocarbons with 4, 5, 6, 7, 8, up to 12 carbon atoms in them. Okay? And the red dots are for regular, and the black dots are for premium gasoline. And now you'll notice that even though you pay a considerable amount more for premium gasoline, it doesn't look like it's all that different. They simply take some of the hexane molecules out of the premium and throw in some extra octane molecules. So what's going on here? Well, we can take those, first of all, those straight chain hydrocarbon molecules and look at the corresponding peroxy radical spectra. And remember, that's how the combustion process in your piston actually works. You go through those chemical steps. And here, bingo, you say, well, gee, this is hexane and this is octane, and I don't see any difference. So I guess they're cheating me with charging more for the premium gas. But if we look a little bit more closely, let me take the octane spectrum and blow it up over here. And now compare it not with hexane, but compare this straight chain octane to a branch chain octane, which looks like that. From that structural diagram, we know that this is a secondary peroxy isomer of the straight chain compound. That simply means that the oxygen moiety replaces one of these hydrogen atoms. It does not replace a hydrogen atom on the terminal carbons. Okay? On the other hand, you can see this spectrum is totally different. We can assign this as coming from the primary isomer, one of these methyl group hydrogens, and this other comparably strong peak from the only tertiary hydrogen here, which is extremely reactive. So we know that we produce a lot of this peroxy species with the oxygen moiety right there. Now let's remember about that chain reaction and what was necessary to make it go forward. The molecule, the peroxy molecule, had to isomerize by grabbing a hydrogen someplace else in the molecule and sticking it on the end to form OOH. That means a ring or bridge had to be formed between this hydrogen and that oxygen. Rings cause strain in chemical bonds. They cost energy. The ones that cost the least amount of energy are 6 and 7 member rings. You can grab a hold of 9 primary hydrogen atoms with a 6 or 7 member ring from isooctane. You're stuck with a 4 or 5 member ring, which is much more strained for if you had hexane there. In fact, the low temperature combustion that occurs in the piston is just not energetic enough to drive it with pentane. So this makes the propagation step much easier and gives you higher performance in your automobile. So that's an example of a practical application. And so now what I'd like to do is I would like to finish up with what I consider to be some of the fun things in molecular spectroscopy. And that is pushing the spectroscopy as far as we can push it and seeing what we can see. And so now this is the ultimate apparatus that was in my laboratory. I think we've got about 6 lasers here. You might remember that I pointed out that the bandwidth in that earlier ring down experiment, the laser was 5 gigahertz. We can now get down to 50 megahertz with this apparatus, which is 100 times higher resolution. So the object here is we want to take higher resolution spectra. We want to see more. We want to put a bigger magnifying glass on this molecule. To do that, we have to make our laser radiation very narrow banded, very high resolution. And so we do that and we send it into what is effectively the same optical cavity that we did before. But it turns out that making our laser high resolution is not good enough. We also have to treat our molecule in a way that makes it high resolution. And now we go back to this point about hot and cold molecules and their quantized energy levels. The distribution of molecules among these energy levels is determined by the Boltzmann equation. We don't have to go into the details here. But the single point is that if a molecule is hot, that the largest number of molecules is always in the lowest possible level. But the number that is in these higher levels fall off quite slowly. If the molecule is cold, then the number in the higher levels fall off very rapidly. We're going to get spectral transitions from the hot molecule from every one of these levels. So we've got another factor of 10 or 100 multiplied by that factor of 1,000 we got from going from an atom to a molecule. And frankly, these lines just get too close together to resolve, all right, if we have all of these levels populated. So we've got to cool the molecule off. And when I say cool the molecule off, I mean really cool the molecule off. We have to redesign how we make it. We're going to use a slit jet discharge. We're going to use a discharge slit. And all that means is we're going to carry out the chemistry in this area. And rather than use excimer laser photons, we're going to use electrons to initialize that chemistry. But we're going to do something else, and that's the key thing. A gas, when it expands, when it goes from high pressure to low pressure, adiabatically, it cools dramatically. One example of this is if you've been to the dermatologist and has a little growth that you want removed, they freeze it typically. And in the past, they often used liquid nitrogen to do this. Sometimes today, they will pull out an aerosol can from the shelf, squirt it, and all of a sudden you'll feel a very cold spot on your skin and realize that they have just frozen it off. That's an example of an expansion and the gas cools. The gas pressure inside the can was several atmospheres. It's 1 atmosphere outside the can. You probably drop the temperature from maybe 30, 50 degrees centigrade from room temperature. Room temperature in Kelvin is 300. We're going to try to go down to the order of 15 Kelvin, within 15 degrees of absolute zero. And so now, we're going to come back to this spectrum of methyl peroxy. I simply show you that because I'm going to do a switch on you. For technical reasons, I'm going to change my hydrogen isotope to deuterium. Here it is, but it looks very much, the spectrum for all practical purposes is the same. And now we're going to take the spectrum of this molecule in our free jet supersonic expansion. And I'm going to blow up this region of the spectrum, all right? Just this very small part. And when I do that, I resolve it into more than 1,000 lines, most of which are due to single electronic, vibrational, rotational transition. And now I'm going to do it once again. I am going to look in even more detail at this region and that region of the spectrum. And here you can see each one of these individual lines. This is the left-hand side, and this is the right-hand side. And what's really interesting is I have a simulation of this, which turns out the simulated temperature, the temperature which best simulated it was 14 degrees Kelvin. But it matches. It matches essentially exactly. And that's because we have performed the calculations based upon the quantum mechanical behavior of the nuclei, the vibrational and rotational behavior of the nuclei. We haven't included in this the quantum mechanical calculations of the electronic behavior. What we've done is we've actually used the electronic parameters as fitting parameters to produce that simulation. So we've got about a dozen fitting parameters here, which we fit and are able to reproduce the spectrum very well. Well, what about just calculating those parameters? Well, this shows that you can calculate these parameters within 1% or so now. That's fantastic compared to 20 years ago. Orders of magnitude better for this kind of molecule. And so one can hope in a not too distant future that we will be able to add a couple more significant figures to the calculation, which would be what is necessary so that we could actually predict these parameters so that we could simulate that spectrum entirely from the fundamental principles of quantum physics. And so with that, I would like to wrap up with just a slide on what I consider to be the very positive future of molecular spectroscopy. First of all, there are new and better spectrometers coming along, which really means new and better lasers. The spectra which I've shown you up to now, basically we selected from the laser a very narrow bandwidth of light, and then by manipulating the laser cavity, moved the frequency, changed the frequency of that light. So we did an experiment which took a long time because we had to move that frequency from here to here to here to here to here, okay? The frequency combs will give you 1 million of those lasers operating all at once. So they will cover the entire room, not all the time, instantaneously. So the frequency combs will put spectroscopy, molecular spectroscopy, squarely in the big data category. The other thing is talking about cavity ring down spectroscopy, which is a particular variant which is useful for these experiments. You can make extremely small cavity ring down spectrometers now, faster, lighter, and smaller. And these have actually been flown on drones over oil fields to find out what gases are coming out of the field or leaking out while they're drilling or while the production is going on, and so on and so forth. You can imagine other places they could be flown that detect gases, etc. So there's going to be no shortage of new things to do with these spectrometers and new spectra that will come out. And then the other thing, which I'm spending most of my time these days with, is the synergy with computations, the big data, the analysis of experimental spectra by artificial intelligence. And what I was alluding to just at that very end was a first principles calculation of spectra from the fundamental quantum physics equations governing the motion of the nuclei and the electrons. And so what I want to do is wrap things up here, but it would be certainly remiss of me if I did not do one other thing before I conclude, and that is, yeah, okay, of course, a little bit more complicated than it should be, but that's okay. I want to thank all the people that have contributed to the work in my laboratory, the graduate students, the undergraduate students, the postdoc, the lab visitors, and on another slide there, the funding agencies which have supported this work. And so this should just circulate through. And with that, I thank you very much for your attention, and we'll be happy to answer any questions.
Looking at the diagram that you have in front, actually, what great distances, how far in terms of light years can one carry out molecular spectroscopy?
As long as you have a bright enough light behind it, in other words, a bright enough star or a galaxy even, then it completely depends upon that, okay? But you're talking about hundreds of thousands or millions of light years.
But the universe is 94 billion light years.
Yes.
So
Yeah.
how far can we get?
Well, I think that
Billions of light years?
if you've got a source out there that's bright enough, yes.
I can help with that.
Okay, yes, you can.
Yeah, we regularly explore gas and absorption at the redshifts of a very distant known galaxy. So we can observe galaxies as they were when the universe was roughly 1 billion years old or less. So yeah, basically we can do spectroscopy across the entire universe.
And in fact, I should have realized that because you've got such huge redshifts on lines like from the hydrogen molecule, that they do go back.
Yeah,
To the-
I mean, we're in an odd situation. We're looking at the Lyman lines in the infrared.
Yes.
So I had a question.
Yes.
When you supercool your samples by expanding, that means that you have to increase your column by basically the same factor to have the same probability of absorption. So how do you do that? Because you're already really pushing it when you have these 0.001% chance of light being absorbed at the mirror.
No, you don't have to increase your column.
Oh, okay. So
Because what you're doing is you're taking 100,000 lines and putting all the molecules into absorbing on 20 lines.
all right.
So that's what you're
So
doing.
the population of the lower states is just so high.
That's exactly right.
Okay, great. Thank you.
I could ask a question.
Sure.
A really simple question, probably. From way back when you were showing the waves, all the waves and they were getting closer and closer and closer together.
Yes.
You chopped off the ones, I understand why you chopped the ones off at the beginning that were too far apart. But why did you chop the ones off on the other one? The ones that were really, really close?
Why did I chop them off?
Well, you said, well, I'm only going to consider the ones.
Oh, because, okay, let's see if we can, we won't go back. I'll let you keep looking at the students who did all the work, okay? What I said was that light, what we're going to consider today is this region of the spectrum where molecules absorb radiation, okay? In other words, molecules, by and large, do not absorb radiation in the gamma ray region of the spectrum. There are some caveats on that statement, but typical molecular spectroscopy, if a molecule A managed to absorb a gamma ray, and the probability for that happening would be extraordinarily small, but if it did manage to do it, molecules just blow apart. Got way too much energy, okay? And so that's basically what's happening. If you notice that the spectrum, there was a bar higher up on it that labeled part of the spectrum as non-ionizing radiation and another part as ionizing radiation, okay? Ionizing radiation is what's really bad for human beings and that sort of thing. But reason why it's really bad is it kicks electrons out of molecules. So you have free electrons that can go along and bang into DNA molecules and break them up and cause all kinds of havoc. And so we were way deep into the ionizing radiation.
Just a quick question. All the molecules you analyzed were relatively small. Is there a limit in the size of molecules that this technology can address?
There always is a limit.
Well, I guess
And-
what is the limit?
Yeah. We have certainly looked at molecules that had 25 or 35 atoms in them, okay? It's by pushing experiments in the way that we pushed them right at the end, where you have higher resolution and cool all of those molecules down into a few quantum states, that you can extend the size of the molecule you can look at. And how far we can go, I don't know. I'm certainly not proposing that we're going to be able to look at proteins. But you know, the kinds of problems which we focused upon are driven by these small molecules.
One more question, anything?
Nothing in science. You mentioned uses of the technique, flying drones over oil fields to find out what's coming off the oil field. Arcane, could you see spying uses of this? Other production of weapons and other things where we could find out a lot by not needing anybody on the ground, simply being in the air?
Well, without revealing classified information, it's being done. It is being done.
Oh, it's not yet. Okay. Thank you.
Did I see one more over there? I don't want to. One more question, and then
Yes.
we'll keep Terry afterwards.
Since you can observe all this very detailed chemistry with hydrocarbon and, you know, radical formation, upper atmosphere, etc., can you actually affect, maybe with the high energy lasers, the composition of and the branching mechanism that occurs, so you can do pollution control in some way? So it's kind of taking to the next way, the control level.
Yes, I mean, control is essentially the other part of the Holy Grail. Predicting is how chemical reactions will occur, quote unquote, naturally, is one part. The other part is how to affect them, okay? And it turns out that the sort of spectroscopy I've been talking to you about today, the high precision spectroscopy, is relevant to the predicting business. There's another kind of spectroscopy which is called ultra-fast spectroscopy, and I collaborate with a couple people in physics on some of the experiments like that. But if you want to control, then you want very short pulses of energy and at very specific times. And that comes from having lasers which actually give out photons for amounts of times in the picosecond and the femtosecond domain.
Well, I want to thank you for a really interesting talk. I think it's really enriched our life on knowing about this, and we thank you so for your time. Stay, I have a couple of items of business for the Academy, but stay, and I know Terry will be happy to answer more questions. Let's thank Terry.